Hey everybody, I think we got all the music off. We got Vincent here. How many questions will be on the exam? I think there's like 40 or 50 for 201. And Daniel's talking about we're going to do some interpretations. You bet. I think Mubot's a way to people are going to check those points. Mubot wasn't awake a second ago, but Mubot's awake right now. We'll throw out a little bit of points. Why not? 10 points. We never hit the 10 point button. Oh, let's say, hey Josh, good to see you here. Let me get off top chat, go to live chat. I'm replying to all the emails. So if you've emailed me or Discorded me, I'm trying to keep up with everything. Don't worry. Keeping up, getting those messages, hopping online here. There is multiple choice, numeric entry on all of our exams. A lot of it's multiple choice numeric entry, some interpretations. And let's talk about those BAS 320 interpretations. Here we go, BAS 320. We're starting off with your stuff right here. But if you have questions, let me know. We're going to go through do the BAS 320 interpretations. How can you get a correlation from VILF when you get a chance? Oh, is that on the exam? Oh, that was a midterm question, wasn't it, Josh? That was a midterm question. I could do an example of that. Let's hop over here and do some interpretations. I agree with Life of Gens right there. For 201, Canvas content, such a good way to review. Literally, they come from the test question pools. So if you when you're doing Canvas content, if you're like, I got this, I know this, you're on track. So we don't want people to be blindsided by the exam. We want for 201, you see a bunch of Canvas contents, and they basically let you kind of track to see like if I can do the Canvas contents and I'm understanding them and I don't need my notes, I'm good. Now, if you have to look up everything in the Canvas content and it takes a long while, then you want to make sure you're studying. So the Canvas contents are a good way, but the more you treat the Canvas content like the exam where you don't have notes, and which you do have notes during Canvas content though. So yeah, Josh, we could talk about that. Here, let's hop to interpretations. Okay. So let's do some interpretations right here. This is BAS 320. Let's put a note top screen. BAS 320 interpretations. And really, you'll notice some themes right here. You can view the ones you took. You can view the Canvas contents you took. Thank you for all the questions, everybody. Love the chat. So people are checking their points as we're talking right here. So one thing we really need to distinguish between here is question one. Are we doing simple or multiple? Now, if we are doing multiple regression, so when we do multiple, we must say what? So what must we add in like here? What would we be adding in when we do a multiple regression? So if we do a multiple regression, we would add in what? What we would add in some sort of like lingo right here that we would say like, but what? I hope so. We were talking about that this morning about me flying in. Hopefully the world's a little bit more normal. I won't be back like for total in person, but I will be back in like a year and a half. So, but I hope to fly in and say hey to everybody. If you see me on campus, be like, hey, Brian. I'll be like, hey, what's up? Who are you? And then we'll talk and have a normal conversation. Who here in 320 knows when we do multiple regression, when we do multiple, what do we do? What do we do? So there's an important phrase with multiple regression. In multiple regression, we have to acknowledge that the other variables are held constant. And this is where otherwise identical, exactly. The otherwise identical is so key right there. Thank you so much. We're throwing out little points today. Little bits. Otherwise identical. The otherwise identical is huge right there. Little points today. So we are like, I don't know. Join in, say hey. There's not tons of points, but we'll keep throwing little points. Otherwise identical. This is key right here. And I think no better example works for this than, I think it's the body weight data set really makes this clear why we're saying otherwise identical. Now, if you're wondering, it's the other body weight data set, I think. There we go. Let's clear that out. Let's rerun it and let's load the data. These are data found inside of reg class. Maybe like an hour and a half, 2 hours. We'll see. Semester. Crazy semester, right? Throw those questions in the chat, Hunter, and we'll try to get to them. So we have here the body fat data set. I want you to just think, does this make sense? Like just look at the data and think what's going on right here. We talked to someone and they said my body fat is 6.9%. That's pretty crazy low. They're 22 years old. They weigh 173 pounds. They're very precise in their height measurement. They're 6 1/4 of an inch, 6 foot and 1/4 of an inch, 3.6 inches. So you've got all these different measurements right here on this individual, like whether it be their chest, their neck, these different measurements right here. Hey, Lindsay, great to see you here. So just think about each of these as a person right here. So what we're going to do is we're going to go in and make a model right now. We're going to call it Model M. That just stands for what we're saving into. If anyone's watching who's not in 320, We're going to call linear model, so we're using linear methods, fitting lines. And we're going to predict the body fat, and that is the Y variable. Now, it's not capitalized because it's inside of this data frame. The F is capitalized of body fat, though. Not on Canvas yet. Extra credits are not added in yet. How do you find rank in the Discord chat? Rank in the Discord chat. So you want to go in and go to the rank check channel and check it out there. And then we want to go here and do dot. Oh, what up, Tyler? So good to see you. You know we've got that new intro, Tyler. I finally got it done. We've got you in the intro. And there it is. Let's take a look. Now, here's why the otherwise identical is so important. Because I want you to notice this. Weight has a what relationship to body fat? This is the key thing that statistics is important. I would say until the night of the final, till like the final's over. I'm probably gonna call it on like, hey, final's over, class is over. So like tomorrow night. Yep. What do you notice here about weight's coefficient, which is very important? I like that right there. It's negative. Great job, Nathan, right there. Some more 10 points in the job. We're doing small points today. So I gotta restart the semester. It's negative. The coefficient of weight is negative. So if someone said they wanted to lose body fat, the really bad interpretation would be gain weight because it's negatively associated with body fat. Does that make sense right there? Like, but here's the thing. If you do the proper interpretation from our class, it makes perfect sense. So let's interpret this. And so let's make this very clear. Quantitative Y and quantitative X. Okay. So now when we interpret this is for a quantitative Y. And what do I mean when I'm saying quantitative Y? This all goes back to 201. If you're a 201, this applies to you being like, well, we're doing regression right here because we have a QQ. We have a quantitative Y, quantitative X. Because what? How do I know? Just explain to me. Because you have to know these things when you're interpreting. You have to be like, oh, that's a quantitative Y. Just tell me about it. Just look at it and tell me, be like, well, yeah, that is this. So what are we looking at right there? Like, how do we know it's a quantitative Y and quantitative X? I'm going to interpret this down here, and then I'm looking at this down here, and I'd have to know this to interpret it properly. I have to know this about that, and this about this down here, because the X's are in the model. The X's explain. I think Daniel, I'm going to literally copy paste. We kind of have a... I can go show you that afterwards, Campbell. I can go to the Discord and kind of show you. Let me go to a new Word document. Two observations that are otherwise identical but differ in X by 1 unit are expected from Y by BI units, which is the coefficient right there, where the observation with the higher X is expected to have the higher/lower Y, depending if it's positive. Daniel, great. That is literally verbatim it. So we're going to use what was written here. And you know what I'm probably going to do? I'm probably going to bring this all over to a RMD file. So let me go to an R Markdown file. And what I can do with an R Markdown file is I can actually put the code in here that we're working with. We're just going to delete out all of this. And we're going to put in an R chunk for the code we have been working with. And then we can go down here and actually write our interpretation. It'll look a little bit better. So we'll take Daniel's interpretation right here and bring this back over to the RMD to where we have basically our own Word document and we can see what Daniel wrote right now. So Daniel gave the kind of general interpretation, which is key right there. Now, that's not what you would write on the test because we need context. We need context for this. So this is when we have a quantitative Y and a quantitative X, and that's because body fat is quantitative. How much is your body fat? And weight is quantitative. How much do you weigh? Two people who are otherwise identical but differ in their weight by 1 pound are expected to differ in body fat by 0.08 units with the individual with less weight. Oh, careful with the wills. Careful with the wills. And then remember, it's negative. Tyler, I'm super impressed because I think you've taken the class and you're remembering it. You're very close. There are response questions on 201. I think pretty much all of them are expected. Yep. And then Tyler's super close. Just remember it's a negative coefficient. So the person who weighs more, so let's write it out right here. You ready? I click the screen. So here we go. Two individuals, so we'll go with individuals, that are otherwise identical but differ in their weight by 1 pound are expected to differ in their body fat by, and then the coefficient of it was, here's the coefficient of body fat right there. And this is a percent only because body fat is a percent. This is a percent only because body fat is a percent. And then where the individual with more weight who weighs more. Now, why is it? There are some, I think there is some fill in the blanks, definitely some interpretations, hence what we're doing right now. Why is it that we're saying the individual who weighs more is expected to have lower body fat? And then let's look at the otherwise identical component of this. Why is it that we would say the individual who weighs more is expected to have lower body fat? Why? Why? Because it's negative, exactly. So when people weigh more and they're otherwise identical, we expect them to have lower body fat. So is the advice to somebody, if you want to lose body fat, gain weight? Well, logically, you would think that if someone weighs more, you would expect them. But here's why it's negative right here, Daniel. Does that make sense? It's negative because as body fat increases, we actually expect, as weight increases between two individuals, two people, or as weight, and Olivia's figuring it out right there. Because that actually goes to the otherwise identical component. Because this is not about somebody changing. That's one of the things we maybe get wrong in 201. I don't love about it. We're not talking about if someone changes. We're talking about two people. So there's a Brian out there that exists who is the same age as me, the same height as me, the same neck measurement, same chest, same abdomen measurement, but this Brian weighs 50 pounds more. He has all the same measurements as this Brian. What do you think that Brian would look like? What do you think that Brian would look like? He has all the same measurements of me. His chest, his abdomen, his arms, which would be funny if they were the same measurement, but somehow he has all the same measurements, but he weighs 50 pounds more than me. He's another person who is otherwise identical, but weighs more than me. So think about that. He's a person, he'd look like me, but think about his body fat. This is a person who is otherwise identical to me, but weighs 50 pounds more. Zeus. I think Olivia was hitting the nail on the head right there, because to be otherwise identical, pure muscle. To be, but no, he would be a lot more muscular, right? Like he'd have to be more dense because he would be Hulk Hogan or something, because he's otherwise identical to me. He's like the same age, the same height, the same measurements. Like he's the same everything, but he weighs more than me. He swallowed. Oh, I love it, Emery. That is the best. I think it's Dr. Emery right there. Emery just killed me right there. No, that's awesome. He swallowed some iron. That's how we would explain it right there. So two individuals who are otherwise identical, but are otherwise identical, but different. So what we're thinking here is we're manipulating, and it's not that we're talking about change. We just have two people, person A, person B. And what do we expect the difference to be? Now, unfortunately, who's not invited to the party? Tyler, you're invited to our party. But what four-letter word do we not like to see in these interpretations which imply cause and effect? Get this word out of your vocabulary when it comes to statistics. It sounds very cause and effect. Sorry, Will. But Will, you're not going to be here for this. We expect, and Olivia, you might be talking about 201, and we'd almost expect, this is almost null hypothesis-y, rip my boy Will. We expect there to be no difference. So here's the issue. If you think about all the combinations of things you might have to deal with, so this is 320 oriented, great job 320, I want you to just permutate the options right here. And if you permutate the options, how many combinations can you come up with? And I'll let you choose the next direction we go. But if you start permutating the options of what you have right there with quant and cat, what's another option, and how many would there be that you should probably be pretty versed on? So how many permutations of quant cats are there? Think the Y and the X. So I'm asking you, you're going to have to know a few of these and know how they change and why they change. And we'll talk over them, and this was a quantitative Y and quantitative X example. But what's another combination, and how many total combinations are there? And it's good just like to understand what we have, and then you can say like, oh, this is the way this problem is. This is how I would interpret it, because it's going to change it, especially drastically when it hits the Y. So what else would we have? Tyler just crushing it. Tyler, former student. So Lurka, we wouldn't do a YY model. And don't worry, Lurka, good points there too. We're just talking about small points today, all those. Little bits. So quant Y, cat Y, quant X. Yes, Tyler actually listed all the other versions. So Tyler did all the other permutations. Which one would people like to do? I'm going to let you choose, and I'll come up with an example, but I want you to tell me a version you want me to do. I'll come up with an example of it. So this is where, if you know it this way and you can be like, oh, well, maybe I should practice interpreting one like this and see if I get something right, then you're on the right track. Which one do you want to do? Tyler came up with Tyler, look at Tyler wrote right there. And Tyler, so great to have you here. Quant Y with a categorical X. So, and thank you, Ansley, right there. Great suggestion. So with this right here, and then Lurkus wants the next one. So what is this going to do? What are we going to get from this? Are we doing linear regression, yes or no? Just a Y or N in the chat. Are we doing linear regression right now? Are we doing linear regression right now? Y or N? Are we doing linear regression? Are we in the realm of linear regression with this one? So we say, okay, we're doing a quantitative Y with a categorical X. We are doing linear regression. We are. And why are we doing linear regression? Well, I know we're adding a little extra salt bay on there. Oh, but wait, careful. Yes, people are. Oh no, don't worry. We're throwing the big points. We lowered the points today. Kayla, some points. No, that's a good thing. So the big thing to notice, and great job, Kayla. Kayla, great job being here practicing this. And people are saying it. We are doing linear regression, and people are putting in the chat, quantitative Y is linear regression. So we've said we're going to do a quantitative Y and a categorical X. Now the categorical X means what? So let's put here notes. We're just adding notes. Quant Y, linear regression. But what's the categorical X going to do? Categorical X means we're going to deal with what's. Oh, I love it. We're going to be copying. Yes, Kayla, yes. Kayla, great job. Have that written down. That's going to help a ton for 320. Preparing for next semester. Lurkus got it. And that means we're dealing with indicators. So we're going to be dealing with indicators. Does that make sense? We have indicators in a logistic regression. So we have a lot of ways to talk about this. We just need to do indicators. What if we were to say, let's go here to data survey 10 and let's predict, let's go and make a model predicting, this is going to totally work, somebody's weight based on their height, whatever that is, plus their handedness. I want to know how much somebody weighs, and let's say, okay, you're right-handed, you weigh this. So not quite different slopes yet. Different, so Hunter, great answer right there. Not different slopes. That'd be if there was an interaction. Hunter, great follow-up. Yep, Hunter, you are correct. And great practice. So, and one of the best things to do is probably to visualize your model. This one can be visualized. Some of them with a lot of variables can't be visualized. So, and actually, you know what's interesting? I can actually tell you, this is a little advanced. Let me ask you this. How many indicators, great job, Campbell, right there. How many, you're currently, Tyler, yeah, because you took 201 with me, but you're not yeah, so Tyler, great practice. So thank you, Tyler, for being here. How many indicators are in this model? This is a good basic question. I'm not giving you the right answer right now, but how many indicators are in this model? How many indicators? Thank you, Campbell, right there. How many indicators? This is not the right answer. How many indicators? 2. Why is it 2? There are 2 indicators. That is correct. There are 2 indicators because there's 1 reference. Daniel, great job right there. So Kayla, this is the way, and we'll practice right here. If there's 7 days of the week, everyone put in the chat, how many indicators would there be? So if there's 7 days of the week, how many indicators would be? Because the indicators are the difference from the 1 reference level. There would be 6. If there's 12 months of the year, there'd be how many indicators? If there's 12 months of the year, there'd be how many indicators? There'd be 11 indicators. And technically, it's K-1 technically formulaically. Josh, thank you, and great advice right there. Or is it L minus? I think it's L-1. I think because L for levels. So it's the amount of levels minus 1. So you just say, how many levels are there? There are 3 levels to handedness. And then you take and you subtract the 1. Now we should know, and the graphic helps us, the reference level is always the what alphabetically. So what is going to be the reference level? The reference level is always the what alphabetically. So you can see it, I'm pointing to it. And so it's always the what alphabetically. And not always, in linear it won't matter here. Great job, Lurker, right there. Linear is not don't worry, because you can do it for logistic too. And then, but In logistic, that's when we deal with it. We'll talk about that here soon. This is just for reference levels for X's that are categorical. And when you're doing any reference level for any model, whenever there's a reference level, it's always going to be the first alphabetical, the first for reference levels. Does that make sense? And then Daniel, take the note Daniel has in the chat. He says reference level is first for categorical X's. Logistic is level of interest is last. And logistic is the level of interest, which is last. Logistic, level of interest, last in logistic. And we'll be reviewing that more here in a moment. But let's ask the questions again, just to nail it down. You have to do a bunch of examples. What is the reference day of the week? Think Monday, Tuesday, Wednesday, Thursday, Friday, Saturday, Sunday. What is the first alphabetical day of the week? So if we do the days of the week, the reference would be Friday. What is the reference month of the year? January, February, March, April, May, June, July. What is the first alphabetical month of the year? That's how the reference will be chosen to compare other months to. It'd be April. Great job, Kayla, right there. Exactly. So that is the reference level. So I want you to just think about one thing right here, and this is where we're going to a little deeper understanding. We will have two coefficients in this model, and both coefficients will be what? We will have two coefficients in this model, and both coefficients for handedness levels will be what? If you understand this, you're understanding something, you can see the output and understand what the coefficients will be. I'll show it and I'll explain it, but we'll have two coefficients, and both coefficients will be this. I can tell you by looking at this, we have two coefficients, one for left, one for right, and both of them will be this. Because we're predicting people's weights, and the weights of left and right are this to ambidextrous. Remember, because we're going to compare it to ambidextrous. We're going to say like the difference between ambidextrous and left. So we're going to compare the left people to ambidextrous people. They'll be negative. Because we're going to say how much difference is a left-handed person than a ambidextrous. Does that make sense why it'll be negative? And the most negative coefficient will be left. So let's go ahead and I'm going to literally copy paste what Daniel has in there. But I think Daniel's asking. So what interpretation do we need to know though? Yeah, and yeah, so I'm going to go through all of them right here, Daniel, because I think you literally gave us the interpretation. Daniel literally wrote this, and let's use it. I'm going to put 1 minute on the clock right here. I want you to try to write the interpretation for right-handed people. This is your practice. If you can do this, you're doing well. Take a moment. 1 minute on the clock. I can write the interpretation, but can you? This is one of the ones you'd need to know, Daniel. And then we'll do logistic after this, because then we have to switch up the way in which we're interpreting. Take a moment. 1 minute on the clock. 45 seconds to go. Try writing it. We've got the... Let me double check it. Two illustrations that are otherwise identical. One is a reference and the other is the Unicaro. The one that is Unicaro is expected to be... Oh, BI, that's the subscript. So that's the coefficient. Which, wow, is it almost statistically? It might be, oof, that's another topic, like the drop one topic. Height is statistically significant. Handedness. So a good note right here is height is statistically significant. We don't got to do a drop one on that because it just is. Because the coefficient is its additional information. We'd have to do a drop one here. Wow. Let me start writing the answer. And I think I said right. Okay, so here we go. Two individuals that are otherwise identical because we have a multiple regression, but one is ambidextrous, and the other person is right-handed. The one that is right-handed is expected to weigh 7.5 pounds less. There we go. Who thinks they could do that right there? We're just comparing them. We're just saying, well, if we have two people and one's ambidextrous and one's right-handed, but they're otherwise identical, like they're the same height, which is weird. I don't know what this is. Like ambidextrous people just got two hands. So I don't know. Well, a lot of us have two hands, but I don't know. This is it statistically significant? I'm actually wondering. It's not. It's not statistically significant. Yeah, so we can see both. Oh yeah, let me get the interpretation. Are you talking about this right here? And the coefficient is right here. I think I rounded it. And so we expect two individuals that are otherwise identical. One is ambidextrous and the other is right-handed. The one that is right-handed is expected to weigh 7.5 pounds. The one who's right-handed is less. So it would be the right-handed individual is expected to weigh less. Do you see that right there? Like if you go to it visually and you look at it, you could have two people who are otherwise identical, but one of them is ambidextrous and the other is right. The right-handed individual is expected to weigh this much less. Like you take a person, they both are 65 inches tall. The expected difference between these two individuals, given they're the same height, would be 7.5 pounds in their weight. That's the expected difference. Now, we're not saying it will be. No worries. That's like so small that great. If it's like a 4 point, that'd be like half a point. We don't want to miss it, but yeah, that's where we want to go with that. So no, great job right here. This is also quantitative Y, but we switch it up now. And so tell me another combination right here we could do. So what's another combination we can easily do right here and get another interpretation? So I want you to be thinking through these because what is another way we could go with this? Because we haven't even ventured into this arena, which is the other arena to talk about. So now we need to switch this over. We could do left-handed. Left-handed would just be, we would switch the coefficient right here. And the coefficient would change. And how did I do that? I don't even know. There we go. And there we go. So now we could interpret the left-handed coefficient. There we go. So the left-handed has a more negative coefficient. They're lower. Does that make sense, Ansley, right there? So you can interpret both coefficients. So the meaning of this is that two individuals who are otherwise identical, but one of them is left-handed and the other is ambidextrous. The person who is left-handed is expected to weigh 12.592 pounds less than the person who's... Yeah, Ansley, great question. Thank you for asking that. If it wasn't a multiple regression and just a simple regression, would you... I don't think so. I mean, graders might vary on that. It's kind of like adding something we don't need. In truth, they could, but so you shouldn't. But it's like one of those things. Like it's not a big problem. Does that make sense? Great question right there, Hunter. I'd say that's not a big problem. It's not good, but it's like you shouldn't have added that. And Nathan makes such a great point. Nathan's adding on, and Nathan, thank you so much. More points. Nathan's adding on that if you were to compare the left and the right, what is the expected difference? So now this one's a little bit more complicated. We don't usually do this, but two individuals who are otherwise identical, but one of them is left-handed and one of them is right-handed. The person who is left-handed is expected to weigh about 5 pounds less. And what am I doing by saying about 5 pounds less? Can you see the mathematics I'm doing in my head? That's probably what I would just say to a boss. Once again, these are not statistically significant due to the drop one test. But what have I done right here by saying two individuals who are otherwise identical, but one is left-handed and one is right-handed? The person who is left-handed is expected to weigh about 5 pounds less. What have I done to just do that? And I'm just looking at it to do it. I could do it mathematically, but I'm just like, yeah, it's about 5. Very close to. Very close to. If I cover it up, you can't even really tell because it really is only on the tenths. But does that make sense how I'm doing that? And you can see it here visually that's the difference of, yeah. I think people see that. Those are, I don't interpret those coefficients much. Exactly, 12 minus 7 is 5. And the 12, negative 12 being more negative, the left, otherwise identical individuals. So just kind of seeing that's very important, knowing that we can subtract levels. But now we need to switch this, and we need to change our world. Where do we need to change our world over to? Let's flip our world, turn it upside down. What are we going to do now? What are we going to do? What am I showing you right here? What is this? What's going on? Where are we going to bring our world to that's going to change massively how we think about these things? There's going to be a big change. Yep. Let's go over to categorical. And so we have 2 more permutations to do with a categorical Y and a quantitative X. And because we have a categorical Y now, we are now doing logistic. Heard like someone started a car. I was like, thunder. Sounds like cool. And now we have a quantitative X, which means we're just doing like one coefficient. What I mean by this is when you have a quantitative X in your model, you will just get a coefficient. Does that make sense? So when we put height in the model, The significance of height is the significance of height. You don't have to use the drop 1 for it. You'll get the same p-value because the significance of height is what information it brings with the other variables already in the model. But when you have multiple level categorical x's, which we were just dealing with, you have to do the drop 1 to remove both those levels and compare a model with and without. This is the partial F test via the drop 1. So we cannot tell if handedness is significant until we do the drop 1. But conversely, we can tell if height is significant because it's just one thing. Height is one thing, but handedness has 2 components. You'd have to use the drop 1 partial F to look at a model with and without and see that handedness was not significant. So we're just dealing with one coefficient right here. We're not comparing it to a reference. We're not doing that. So that's what a quantitative Y is. So now we need to switch the model right here to predict somebody's gender. We also need to add something else. Hints for the take home. You need to make sure to do this, GLM. And then we have here family equals binomial. And here's our model. Now, what do you notice this does? What happens between these models? They are just shifting what and what. By changing the intercept, you're changing the 50-50 breakpoint. These implicit equations are just shifting these. Just think of the 2 directions. So the change to the intercept, because there's no interaction right here, the change to the intercept is just shifting them what and what. Thoughts? Left and right. Just shifting it left and right because the intercept is the 50-50 breakpoint. Now I want you to take a look right in here. If I have 2 individuals who are otherwise identical, this person is ambidextrous, I think that person is left-handed, and this person is right-handed. So tell me, great job, Emery, right there. Tell me which of these people, the A, the L, or the R, is the most likely person to be male. Don't worry about how big the probabilities are, but just look at this. We're predicting probability of male because that's what we do in logistic. The level of interest is last. Female, male is last. So if you have 3 individuals right here, ambidextrous, left, and right, who is the person who's most likely to be male? Careful. Remember, we're predicting probability of male. So probability of male is over here. So which of these, comparing these individuals, ambidextrous is the black line, left is the green line, and right is the red line. Which of these would have the highest probabilities? Left is in the middle right here. Right, yep, because it's the highest. Oh, sorry. It is left. It is left. Clarification, because Brian can't read. So, Kayla, you were correct with the way I was stating it. It is left. I just didn't look at the key well enough. So it is the highest line. Does that make sense? It's going to be the highest line, but I missed the key up. The reference level is always the black. Great to see you here, X. Exactly. Kaya said it perfectly right there. So whichever one of these is the highest right here is going to have the higher probability. So think about ambidextrous is the reference. So what will these coefficients be if they increase the probability of somebody being male? So, okay, we won't do that one yet because we'll do height. The easiest thing right here, because we're doing a quantitative X first. Just tell me, go with your brain. If you have 2 people and one person's taller, the person who's taller is what? I've got a friend who's 6 feet tall and I've got a friend who's 5 feet tall. The friend who is 6 feet tall, let's just not even worry about handedness right now, but the friend who's 5 feet tall, yep, and they're what male? So will they be male and so Kayla, this is right. Will they be male or will they be what? More likely to be male. Does that make sense? So, and I think Kayla's going with it right there too. Great job, both of you right there. So let's think about the way the interpretation goes on this, because we're going to compare what again? We're going to compare 2 people. So let's start writing down our blank interpretation to go off of. So we have 2 people, and then we put who are otherwise identical, like they both are the same handedness, because we're not going to move the other variable, but differ in X by 1 unit. The person with the higher X is more/less likely to be level of interest. Take 1 minute, see if you can solve this. I'll throw one of those 100 points again today if somebody solves it. Pretend this is the test. take the coefficient. You got to see the coefficient. Well, hint, hint, hint. Don't look at the coefficient. We'll go here, put that there. Now, this one's tougher. Do not mention, I'm going to give you hints right here. Don't mention the coefficient. Do not mention the coefficient. Who knows the trick? In logistic, we don't mention the coefficient. We only mention its what? Don't mention the don't tell me the coefficient. That's what I mean by don't mention it. Don't tell me that number. You only look at the what of it in logistic. In logistic, you only care about the what of the coefficient. You only care about the what of the coefficient. 4-letter word. I saw the what. Sine. Yep. And Tyler, great job. I think Nathan might got it. 2 individuals who are otherwise identical but different height by 1 foot. You can do 1 foot. You can do that. That's fine. And the base, I mean, all we're basically saying is if somebody's taller than someone else, they're more likely to be male. Like if you don't, like, please use the interpretations. It's a good way to communicate things very accurately. I wouldn't put people who are taller are more likely to be male. Like, you want to make sure you go through this, but that's like the great insight we have in the world is that taller people are more likely to be male. 2 people who are otherwise identical but different height by 1 unit. I would say like inch or something like that. You can say inch or foot. Great job, Matt, right there. The person with the higher height is more likely to be male. Exactly. And great job, everybody. And in logistic, we are getting outputs of what right here. You can see it on the side. And that's why we say more likely. By 1 mile. Hey, it works. 2 people who are otherwise identical but differ in their height by 1 mile. The person who is a mile taller is more likely to be male. It's mathematically accurate. It's probably an extrapolation of the mile. We talked. Yeah, I did say 5 foot and 6 foot. My brain just like jumped to those. I was like, let me think of a tall person. Yeah, no, I did that. No, that you can do foot. I probably wouldn't put mile on the test. I'd probably say we shouldn't put extrapolations of our model because a mile you can't put 2 individuals who would be contained within the scope of the model. You could justify doing a foot because that's within the scope of the model to do a foot. Do you ever interpret the coefficient in logistic? You don't. And the reason is because the change in the model is what? So the change in the model, look at this change right here. It's not what, which means the coefficient, we really can't use it. That's awesome. Why can't we talk about because here's people who differ by only a sign. Yep. And so wait, here's a person who differs by 1 inch to each other. Here's people who differ by 1 inch. What do you notice about, it's not linear, which means it's not constant. Exactly. It's not a constant change. If you go back to our previous models, the people who differ by 1 inch right here, there's a constant unit change or there's a constant difference. Does that make sense? So in the linear models, which you are correct, it's because it's not linear, and linear models have a constant change where these models right here with the sigmoidal S shape don't have a constant change. So we can't mention the coefficient because it won't make sense. We're not talking about a difference in probability of this amount. It is true, the further the coefficient is away from 0, the sharper the sigmoidal curve. So when we have a higher coefficient, there is a more drastic change that the curve will suddenly shift upwards. But this is a non-constant model. It is bound by 0 and 1. And so the sigmoidal curve cannot use the coefficient in its interpretation. We can only talk about the sign, which tells us sigmoidal up in this instance, meaning the probability increases when we see 2 individuals differ their height by 1 inch. So that's really awesome right here. Hopefully this makes more sense. 2 people who are otherwise going to differ in 2 observations. Just make sure if it's people, you don't the observation. We're going kind of skeleton interpretations. So 2 people who are otherwise identical but differ in height by 1 inch. The person who is taller is more likely to be male. Now, how did we know we were predicting male right here? Oh, I hope you did well, 2x. How did we know we're predicting male right here? Why not predict female? What's going on here? How do we know we're predicting male? Like, what's going on with this? Why are we predicting male? It means 2 level. You can do, I think Nathan and I are talking about this, multinomial logistic. We don't do it. It's fine. It's just a different type of model. But binomial means 2 levels. So like binomial. And so we're doing binomial models right here. Hence family equals binomial. So why are we predicting male? It's a level of interest. And why? So that's when we do quantitative wise, there's a level of interest. And in logistic, the level of interest is, finish my sentence. In logistic, the level of interest is what? In logistic, the level of interest is last. Logistic level of interest is last. So we're just saying last alphabetically. Female, male, we're predicting male. It's very arbitrary. You can switch it around. You can reassign stuff. But just the way it works is the level of interest is last. So we are predicting probability of somebody being male. And yeah. So now the only other one we have to do right here to complete everything is now we need to do what? What interpretations have we not done? What interpretation have we not done? For Q8, I'm assuming the Q8. Yes, correct. Yep, great question. Taylor right there. Thanks for asking. 10 points. You are correct. Kayla, thank you so much for... I don't know if Kayla's still here, but Kayla, thank you so much. Oh, and here you do points. On Discord, you do rank. So, and I'm keeping up with all those messages. Woo, woo. Busy end of the semester. Things are exploding the break, and we're just putting them back together. Had to remake the Stats 1 exam. Ah! Oh, man, gonna eat some lunch after this. Ah. Okay. What do we have? Oh, Ainsley, thank you so much. Thank you so much, everybody. I got to bed 2 a.m. last night. We'll sleep. Stat 1 exploded. We fixed it, though. What are we missing? What are we missing? What are we missing? We're missing one last interpretation we haven't done yet. It is on the screen to be done. We're missing one last interpretation. Which, think about this in review. We started off by doing quantitative. I think we did that right here. No, where's our quantitative? Here's quantitative. We did quantitative. I missed by... We did quantitative. Then we did quantitative Y, categorical X. And then we switched to logistic. Good switch right here. And did categorical Y with quantitative X. And now we need to go down here and switch the X. Great job, Tyler, right there. Switching this over to a categorical. And that means we're back over here again to doing indicators. So if you look, what are the indicators in this model? Can you see where there are categorical X's right here? And there's indicators in this model. Where are there indicators in this model? Where are there indicators in this model? Like, oh, this variable brings in indicators. Like, here, I'll let you see the output, and you can see it in the model. But this is creating indicators because we're going to have to compare to the reference level. So where are the indicators being created? Remember, indicators are created when we bring in a categorical X. So you can see, and then we have to compare to the reference level these other levels. We have to say, well, here's the difference between these levels. Handedness. And you notice the variable handedness is up here, but when it goes into the model, it creates indicator variables. So we have to compare somebody who is right-handed to ambidextrous. We have to compare someone who is left-handed to ambidextrous. Now notice that the reference level is actually the what level. It might be hard to see right here. I want kind of a word that means this or this. The reference level is the whatest of these. The reference level is the whatest of these. A word that means like this or this. The reference level, which is ambidextrous, is the whatest of these levels right here. So the reference level is the whatest of these levels. The lowest. So that means the coefficients for the other levels, because they're going to have a higher probability, must be what? Because if we compare two individuals, the people who are left or the people who are right are going to have what coefficients? Since it has the lowest probability for the reference level, the coefficients for the other ones mathematically should be what? They would be positive, exactly. And the biggest one is going to be left-handed. They're going to be positive. So when you go over here and you look, you see, yep, positive coefficients. And we're going to have a very similar interpretation right here. I'm literally going to copy paste this interpretation. It's literally, so two individuals are otherwise identical, but one is reference level and other is indicator. The person who is indicator is more or is more less likely to be the level of interest. So take a moment right here again. Can you solve it out? You can talk about left or right. Either one's fine. Let me get them all on the screen right here. There's the output. There's the interpretation. Just remember, it's not observations at this point. We should talk about people because we're stat to 1 students if you want. But what do we have going on right here? You be the hacker man today. You do it. You got this. What do you think? Take a moment, try to solve it. See what people come up with. I made a really good, like, we had some like potato stuff and I was like, let me use this last night. Let me use my tofu chicken. I'll give it 15 more seconds. Interpret either this coefficient or this coefficient. Good practice. So when you get to test, you're like, psh, I've written this out a bunch of times. Psh, easy question. Nice and fun. 2 people who are otherwise identical. One is ambidextrous, and the other is left-handed. The person who's left-handed is more likely to be male. Just the expected. Just Tyler, such a great job. I'm literally going to copy paste this. Just take out that expected word right there. Boom. Tyler, points in the chat. Nice job. Song ending here in a second. That's got 2 people who are otherwise identical, but one person is ambidextrous and the other person is left-handed. The person who is left-handed is more likely to be male. And we'd expect them to be more male. I don't know. We wouldn't say that. Like, no, you did a great job. I mean, on the test, you get to like curate your answer. I was giving a time frame right there to give it. No, that's a great answer, Tyler. Great job. Yeah, that's where we want people at, is like, you're doing it right there. Like 2 people who are otherwise identical, but one is ambidextrous and one is left-handed. The person who is left-handed is more likely to be male. That's got it. And you just want to think about, does it make sense? You want to view it, especially if you can view it. You can't view everything on the test. But if you're looking at these things, you just want to say like, okay, wait, I got a person who's left-handed. That's the red one right there. And I got a person who's ambidextrous. They do have a higher probability. And they're the same height. That's what we mean by otherwise identical. It's like, okay, they're the same height. So, because wait, what if I have a person who's left-handed and that left-handed person is 5 feet tall, and then I have an ambidextrous person who's 6'3"? At this point, which of these people would be more likely to be male? And you can use the model. So if I have a person who's left-handed and I have and then I'll explain that in a second, Ansley. Good question. So if I have a person who's left-handed and they're 5 feet tall, and I have a person who's 6 feet tall and ambidextrous, who's more likely to be male? The 6 foot tall person or the 5 foot tall person? I have a left-handed person who is 5 feet tall and a right-handed person, or an ambidextrous person up here. It'd be this person up here. So what do we say to fix this problem that the other variables? It doesn't matter. What do we add in multiple regression to say, no. We're just talking about you have a person who's left-handed and a person who's ambidextrous. And then we say, but they're the same height, because we need to say, and we say this in our interpretations, we say what? Like, the other variables we're not comparing. They're otherwise identical. These people are the same height, but one of them is this and the other is this. And in a larger multiple, it'd be like every other variable is constant. There's other ways to say like other variables are constant, given everything else is identical between them. Yeah, so Matt, great job right there. You could say that like 2 individuals who differ in their blah, 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 but everything else between them is identical, like they have the same other characteristics, then the person who is this would be more likely to be this. And so to Ansley's question right there, why male? So the reason we're predicting male is that the question, Ansley, is because it is the last level in female male. So just alphabetically, female, male. Male comes last alphabetically. So when this model makes predictions right here, it predicts the probability of being male. It's a bit arbitrary because it just assigns the one where you're predicting. So this is logistic, correct. And why is it logistic? Big reason why is it logistic. So why is it logistic? Like whenever, and you want to notice this, be like, oh wait, I'm predicting probabilities now because my y is this. And that's the big reason, no, it's logistic. And if you're in tool 1, you're taking this, you can see we like to a lot of you. Categorical y right there, more points in the chat, exactly. That's the big switch, and a lot of people lose points on the test because they go to quantitative interpretations or they don't use the proper model. Now, I'm going to give you a little more difficult of a question. Let's do 1 or 2 questions on this. We might do a little 2 1 after this. But predict Brian's probability of being male. Brian is 75 inches tall. Brian is right-handed. Can you solve this? This is a really, I haven't been throwing 100 points out today. If anyone solves this, we'll put on my favorite song. This is a tough question. This is a question I usually see a lot of people not do well on. Could you solve this? A lot of people have trouble with this one. Yeah, we'll do it next, Josh. You got it. That was like the toughest midterm question right there. I can do that next. I can kind of try to recreate that. Predict Brian's probability of being male. Probably one of the toughest questions. Questions like this, people just... I'll give it a second or two longer. I love this song. What am I giving you up here? I just want one letter in the chat. I'm giving you my whats. I'm just giving you my whats right here. So I've just given you my whats right here. Hunter, I don't think. Good guess, Hunter, good guess. Here's what you can do to check your answer. Brian is 75 inches tall, right? It looks like your answer's... Whoa, Tyler. Does everyone see Tyler's answer? Because it looks like Tyler's answer is kind of near where we should be, right? Because the probability should be close to 100%, right? I'm giving the X's. Nice job, Taylor, right there. I'm giving you your X's. So what do we need to do? We need to write out the equation. We can do it the long way right here. But let's go to the equation. And we are predicting prob male. Oh my gosh. Probability of male. We don't want to underscore. Let's go prob male. Equals to. Here's the coefficient of the intercept. But technically, we're doing logit. More on that in a second. Because Tyler caught it. And then we go here. And that's height. And then we can do it for the right-handed. We're just writing the equation right now. So that's handedness left. So Brian is right-handed. What will HR become? It's a good problem to solve. Brian is right-handed. What will HR become? Brian is right-handed. What will HR become? HR is the handedness right. Brian is right-handed. This is how indicators work. It'll become 1. Great job. That's because we are indicating Brian is right-handed. We write out this. So take a wild guess of what handedness left will become. What do you think handedness left will become? Brian is not left-handed. Brian is not left-handed when we solve his equation. That becomes 0. This is what indicators do. They indicate Brian is right-handed. We put a 1 in. Yes, Brian is right-handed. Now, really quick question. Both of these would be 0. I'll just answer it. If Brian was what? If Brian was this, both of these would be 0 because we would not indicate Brian is right-handed and we would not indicate Brian is left-handed. Both of these would be 0 if Brian was this because then we would be like ambidextrous. Does that make sense? Like these are indicators to say Brian is right-handed, Brian is not left-handed, and if Brian was ambidextrous, both indicators would be 0. But Brian is right-handed, so he has to indicate he's right-handed here. Now, the height coefficient is simply just going to be right here, 75, because that's the coefficient of height. And if I've written this out accurately, what we can do right here is we can solve it now. I think I wrote it in a way that solves, and we get the following. Brian has a 4.6 probability of being male. It's not the way it works. That is the logit. We don't really use that. What we do is we take that, and this is where mistakes are going to happen, and we do e raised to that over 1 plus e raised to that. This is the mistake. Ah, did you find it? Oh, there you go, Hunter. So we do e raised to this. This value is the solve on the regression equation. Like, let me just write regression equation instead of x. That's not an x from the model. That's the regression equation. Whatever the regression equation solves out to, this is the solve of the regression equation. Like that is e raised to your regression equation over 1 plus e raised to your regression equation. So you could, we don't do big problems on it, but these are probably some of the, I'm trying to do some of the toughest problems. But you have to take the answer in logistic and go e raised to the over 1 plus e raised to the. This will bound it by the sigmoidal curve. We go over this in lecture talking about how this creates a sigmoidal curve bound by 0 and 1. Like you cannot plug numbers into this that would give you out something that breaks the sigmoidal curve. So it creates the sigmoidal shape of the what we're trying to predict right here. And so now what we would do is you could just take this value and literally go right here and go and do exp raised to the over 1 plus exp raised to the, and Tyler, I'll take it. You might not have carried all those decimals. I said 100 points. Tyler said, I think 90. What did Tyler say? He was super close. I'll take it as a, Tyler said 98.97. And so, yeah, 99%. Both of our answers rounded. Does that make sense? Does everyone understand what I did right here? All we did was write down the equation. This is like, if you got lost, this is probably one of the toughest problems I can show you right here and explain how to do. Definitely requires a lot of course knowledge on indicator variables, logistic models, and also solving the logistic equation. Probably just, if you solve these kinds of questions, you know exactly what logistic is doing. Toughest problems on the test. If you understood this, you're doing great. If it's rounding, yeah, I just let R do the final rounding because you could literally just take the equation we solved right here and just store this. This is what's so great is you take this right here and you just store it as X. So we're just going to take this whole thing. Sure, we'll do that instead. And you could go right here, store this into X. And so Kayla, if you're unexpected, oh, I had a slash. Does this make sense right here, Kayla, that is now X, and we are now just solving the same thing because that whole equation has been stored into X. And so especially in R, you don't have to do any rounding. It'll do it for you because we could then times this by 100. So let's take this value right here. And we'll just say this, we'll call this prob. Kind of the best things about working with R, you can go prob, and then go prob times 100. And there's that. And then you go ahead and go around here, put one more function, go to round, and you go to 2, and there it is to 2 decimals. Yeah. So we can just like reassign like that whole equation is X. Now run the equation right here where that is X, and then take that probability times by 100 and round it to 2. Awesome. Yeah, and this is the last of the course. So this is as high level as we go, but we do it step by step by step. I think it was so we'll do the other one. You would use that equation. Yes, exactly. Now, if we are doing the other equations, like let's do one more right here, and then we're going to do the other question asked. Solve for Brian's predicted weight. This is way, way easier. So take a moment. Solve. Brian is, once again, you can probably figure it out. Brian is 75 inches tall. And I'm not joking, probably the easiest way to solve this is to not even write the equations, to just think about it. So Brian is 75 inches tall. Brian is right-handed. Solve for Brian's weight. We could do some model building here in a moment. So take a moment. There's some on model building like AIC and knowing. I updated some of the questions to make them a little more clear. Coffee. Solve for Brian's weight. Now this one's just classic linear models. Probably one of the best things to do is to like visualize your model. If you're doing this and you have to solve for it, might be. I'll tell you. Let me see. You have to reorient the window. So you're saying 190-ish? Let me see what it... I'm going to look at the model to get a guess. Okay. You're saying 190-ish. I'm right-handed. Oof. Where's right? It's right here. Maybe. Yeah, it looks about 191. Looks all right. Great job, Hunter, right there. Excellent work. Yeah, it looks about right. All right, so when you write out this model, if you want to write out the full model, we need to go here and go, we're just putting a quantitative y. Height equals 2. The double dollar sign calls LaTeX writing. And then we're going to take the intercept. There's the intercept plus coefficient of height. And I'm just abbreviating height or I'll go way off the screen. There we go. And then minus coefficient. Sure, double minus. That's amazing. Handedness left. And then minus a coefficient handedness right. So when you solve this out now, once again, it works the same way right here. We don't have to do the logistic portion at the end right here. Oh, okay. Let's see who's right. I love this. So we're going to take right here and solve by putting in Brian is right-handed. So this will go to an indicator of 1. Brian is not left-handed. That goes to 0. Brian is 75 inches tall. And literally, we just solve the equation now. This is the answer. Who's going to win right here? What? Okay, I think I did something wrong, everyone. What did I do? That doesn't look right to me. What did I do? Oh, I did. Let me see. Oh, I did a double negative. Oh, no. Oh, wow. 100 points. Yeah, and this is why we do why we look at it, because if we do that, I'm glad I did that error. 191.4273, and that's with all the decimals carried. Like carrying every decimal very exactly, we get this right here. So if you got close to it, don't worry. That's with every decimal carried, and all we're doing. Great job. I love the positivity. So what are we doing to solve this equation? We are taking the coefficients, we are taking the x's, and we're just plugging in and solving. We're just saying plug in and solve, and mistakes happen, obviously. That's why I looked and I was like examining the model to be like, whereabouts should we be at? And if I go up here to the 75, the right-handed line above 200 just didn't make sense. So I wasn't like, oh, it looks like I'm right. I'm like, it doesn't make sense. It doesn't make sense. And what you could do to doubly confirm your answer is you could go right here, and I think we can do this. So we can go to visualize model. Watch this. Visualize model, M, AB line, horizontal equals this, col equals red, purple. We're going purple. There it is right there, and look at that. And we could even confirm if we had one more line in. So AB line, vertical equals 75, and col equals purple. I'm going purple. And where do we see? Look at that right there on the right-handed line. Kind of makes our graphic a little crazy over here. But right there on the right-handed line, this is someone who's 75 inches tall and right-handed, and that confirms that our value here that we are assigning to the horizontal is the value. So you could, if you really wanted to like confirm your answers, you could do things like this. Like if you were taking a test and it's like you want to be really certain of it. And if you made it in a Plotly, which this isn't, you could like zoom in and be like, how decimal place accurate am I? But that confirms we have found the right answer right there. And there's me. There's me right there. But that is my prediction right there according to that line. Now, Brian doesn't weigh 191, kind of a basic question right here, and then we're going to do the other question. Brian doesn't weigh 191. Brian weighs about probably 180 these days. Thus, Brian's residual is what? So Brian weighs about 180 these days. So think Brian is one of these people. I'm probably like down here. No, that's way lower. I'm probably down here-ish. How much do you actually? Yeah, about 180, or I'm like upper 170s. I'll go weigh myself right now. But so yes, 11.4. But what? Be very careful. Anything down here would have a what? So it is like 11.4, but there's an extra little bit. The model is off by about 11.4, but I used 180 because it's a nice, neat number to do. Well, but 11.4, but since I'm below the model, I would have a what? Negative residual, exactly. Concept still carries over here that Brian would have a negative residual. The model over predicts Brian. So I have a negative residual. The model misses me by about 11.4. And yeah. And am I typical for how the model does? Can anyone explain? Is Brian... Ooh. The model does a little bit better or a little bit worse on Brian. What do people think for how this model typically does? Brian, the model is doing better or worse for Brian? Who could, we're going to do the other concept here that I was mentioning about the VIFs. But for how I would say it does a bit better. And how are you assessing that to say, well, the model's actually doing better than Brian than it typically does? Because the model, when it predicts people, typically misses by what? The model typically misses predictions by what? Not 18. Oh, 18 pounds better. Oh, I'll take that right there. Great answer. I'm throwing some points. We're going 50 points on that. Yeah, so Emmer, you are correct. I saw 18 pounds. Like you're saying, it usually misses by, and I'm just one observation, so that's not a full, like, on average. I actually do a little bit better than it does on average. And so if you're wondering what people are looking at, they're looking at the residual standard error, which is how far out the residuals typically are from the model. So the model typically misses. Now that person down there, behind my head over there, did a horrible job. They have a ridiculous residual. But the model typically misses people's predictions by about 30 pounds, which is a pretty big miss. So the model typically misses predicting people's weights by 29.13 pounds. Like when we predict someone's weight, we're usually off by about this amount. That's what a typical miss means. So it did better for me because it missed me by about 11.4 negative, if we say about the sign of the residual. And so our residual standard error does not have a sign to it because it's like a plus or minus on your miss where you're like, I'm usually off by about this amount. And yeah, that's excellent right there. Let's do the other question about the VIFs. Now, VIFs only matter in what kind of models? VIFs only matter in what kind of models? VIFs would only matter in what kind of models? VIFs would only matter in what? Because it's variance inflation. Variance inflation. VIFs would only matter in what kind of model? Well, we can do it for linear, we can do it for logistic. Hint, hint. It would not so much matter in this, and I think we can't even get it from this, so we don't want to do that. Want to go back here. We're not doing... And Kayla, great answers right there. Don't worry. VIFs matter in multiple models. This is just our regular old linear regression we do in Stats 201. I'm thinking if I do VIF, it's going to say, nope. Why is it telling me I can't do variance inflation right here? Because what? What does it mean? Model contains fewer than 2 terms. So it says it can't do variance inflation. Why? And so, oh, does it say viewer? It's simpler. It has 1x. We need, I don't think it's mentioned too much. There's a question. I can't think of a question that has VIF on the test, just saying off the top of my head. I'm not saying it's not on there. I just can't remember as I look through everything. We need multiple x's. Yep. So now if I change this to GPA, take a look, we get variance inflation. Now, this is actually very good. What I see right here is that the variance inflation right here is very small. So inflation is how much something has increased. What is the smallest something could be inflated by a value of what? So it's a percent increase or a factor increase, I should say. What is the smallest something could be inflated in terms of factor inflation? So it's variance inflation factor. So it's a factor increase. Like if I double your salary, it'd be 2. If I triple it, it'd be 3. Now it's not quite 0 because 0 would say there's none. And variance inflation can't decrease the variance. Variance inflation can only go as low as what? The formula for it is 1 over 1 minus r squared. So ask yourself, what is the smallest r squared can be? And so 100's on the right. Because the smallest value of r squared, and not some adjusteds or stuff like that, the smallest value of r squared is what? The smallest value of r squared is what? And this is the formula for variance inflation. The smallest value for r squared would be what? Like the smallest r squared can go is this, like none of the variation, which is the answer. It can be 0. And if you have no overlap between your x's, so actually this is an r squared sub I technically, it's of the ith variable in the model, the r squared of the ith variable. So that would be it right here. That's just how is our x explained by our other x's. That's another concept to go into. But then r squared can approach what? which we won't get an answer if I put in that, but r squared sub I, which is just the r squared for the ith x in the model. We go over these in depth when we go through them, but like I don't know, I could reteach r squared sub I right now if you want. But right here, what is the highest an r squared can go to? This r, any sort of r squared can go as high as what? And so we'll have it approach it here. We won't have it go to it because we might get an issue, or maybe we'll put it to that. R squared approaches what? The highest r squared can go, which is variation explained, goes towards what? What does r squared go towards? Like as we do better models, 1. And so good. It actually did give the answer. Variance inflation goes towards infinity. And you can see right there, that's a little too big. Well, I just want to view it. As you get higher and higher values of your r squared sub I, and so r squared sub I is a bad thing. Does anyone know that crazy huge word that r squared sub I indicates to us? R squared sub I, also variance inflation, is a measure of multi-something. It's how the x's explain the x's, and you don't want your x's explaining the x's. To literally get this, I'll do this in the background while people think this over. I would make a model right here, and this is what r squared sub I is, where my x is the y variable, and my x's explain it. So this is now a model where my height, which was an x variable, is the y. So it's how much of this x variable is explained by my other x variable. So this is an r squared sub I right here. So if I go 1 over 1 minus r squared sub I get that. And you know what that is? Oops. Oh, we saved over our model. That value right there that you just saw is the variance inflation. Now, it might be doing a little more decimal place accuracy on us than we have, but what r squared sub I is it's a bad r squared. It's multicollinearity. It's how is your x from your model, like one of your x's, because it's the ith x. If you have more x's, there'd be more r squared sub i's, but it's how is one of your x's explained by the other x's. So you don't want your x's explaining each other. Put one letter in the chat. You want your x's to explain this thing. You don't want your x's to explain each other. They're not there to explain the other x's. You want them to explain the y exactly. So you don't want your x's to explain your x's. You want your x's to explain your y. So this model right here, which is going to indicate to us the multicollinearity, is when we look at how is height explained by GPA, which both of these in the previous model were the x's. So this would be the r squared sub height. Like you could say this is the r squared of the height, which is just maybe the first variable model. The I just stands for one of the x's. So this, you don't want this to be high. It indicates that your x's are bringing redundant information. And the higher the multicollinearity, the harder the time the variable has to estimate certain coefficients. So I think, I did it during class. I'm trying to remember the exact question. Dr. Panel wrote such a good question. It was pretty tough. I think it was like which of them have the highest correlation, but understanding what these are right here. I think he gave like multiple, I'd have to literally pull up the question. It's such a good question, but he goes over like, here's different models right here. Which of these have the highest correlation? But yeah, so I hope, don't worry, that question doesn't appear on the final. I don't think. It was a really good question, really tough. Even I had to pause. That one took me a minute or so to solve. What additional questions are there? I'm officially out of coffee now. Sad times. Me when I'm out of coffee. No more coffee. Get your yoga. What tricks people feel most on the final? For 320, I would say the switch to logistic. So whenever people get your yogurt. Oh, my yogurt? Oh, I do have one of those key lime yogurts. I should have one of those in a little bit here. I'd say the biggest thing that usually have people a problem with is logistic, because people get so in the theme of doing linear regression, and then they just automatically start using linear regression techniques for logistic. Yeah, I'd say like people just like yogurt. So always identify. Here's our thinking music. Always identify when you're looking at a problem, what are the variables I'm working with? Am I working with a quantitative y, categorical y? Am I looking with a quantitative x, categorical x? And that's big for the interpretations. So check out those. Like, make sure you go step by step by step by step by step. Might head off here in a moment, but good stuff. And just remember, it's just like relax. I don't know. I think people are gonna do pretty well. And it's not the easiest test. VIF and correlation. Oh, with a what about VIF and correlation? So I'm trying to remember. So VIF can give us the correlation. So unless I pull up like Dr. Panel's exact question, which I probably might not put on this video, you're welcome. So when it comes to VIF and correlation, what did I do to my... How did I change this? Let me go to my Windows. My hour is like completely crazy right now. I don't even know what I did to it. Windows. There we go. I hate when that happens. Let's go. We'll talk about that for a moment. I'll stop back to it. So when it comes to VIF and correlation, there's a lot of ways to ask it. And like, I don't want to go into the exact question and try to remember, but no, Dr. Panel wrote such a good question. Oh, it's being weird. That's not good. I saw Loki help us on the... Yeah, it was a tough question. Because I think he was asking like which of those were most correlated. So variance inflation is going to tell us a metric of like, I think he did a model. I think he did multiple models where he ran, I think he did something like this. I think his output was the following. We don't need to visualize for this. And so if I permutate the results, I think he did this, where he did like this. It was a really great question. Like, okay. And then we need to bring this over here. Okay. Okay. So he might have asked something like, awesome, great job, Kayla, right there. We'll be seeing each other again. Yeah, I think so. Might do a 201 stream later tonight. This has been more focused 320. I might label this stream like 320 help. So people know if they're like looking at the channel. Let's go do that now before I forget, because I'm gonna start doing some work after this. Edit video, BAS 320 review, we'll call it. BAS 320 review, final review, because we've really just we'll probably do some more 201 tonight. And thank you for everyone. Always ask those questions. Someone was asking like on Discord, could we do some interpretation? I was like, yeah. So if we were to find, so this is a tough question right here. If you were to find the correlation, because I think that's what his question goes at. If it said find the correlation between the two variables that is the highest, I can tell which two variables instantaneously have the highest correlation. This is a tough question. You have to know the formulas and what's going on right here. We do like some tough questions, not a ton. So we only want a few questions to give you anxiety. Not all the questions on the test are meant to give you anxiety. You gotta have those tough questions. So which two variables right here have the highest correlation? Pretty easy to tell that. Pretty easy to tell which two variables here have the highest correlation. So just think about that. You can put the abbreviation for them, just the first two letters of them. But pretty easy to tell right here with multicollinearity. Well, that's going to give us the R squared sub I, which is a measure of multicollinearity, which is shared variation between the two, which can be measured between R and R squared. So we were probably going to have to do a mathematical formula here in a second. Like we might have to like backwork this. Because height and weight have the highest multicollinearity, highest shared variation. So if it said find the correlation of the highest variables, which could be a very complex question to answer right here with this output, like much harder question. Like first off, you're like, what is this giving me? This is giving me the variance inflation. These formulas right here are the solve of 1 minus R squared sub I. So now let's take this over here and put in the formula equals to 1 over 1 minus R squared. And this is a sub I technically, so R squared sub I. Okay, so when we solve this, what do we need to do? Well, first thing I'm going to do right here is I'm going to flip it. I'm going to take... Does everyone understand why I say flip it? Because you can mathematically flip stuff so that you would get 1 over 1.5655 is equal to 1 minus r squared sub I, and that's over 1, so that's the same right there. Does that make sense right there? And then we need to take and add the r squared to the other side. And that's going to be this right here. It's going to abbreviate that to 1.5. I'm going to carry my decimals at the end. And then you would have over here 1, and then you would subtract. So now we need to go here and go r squared is equal to 1 minus 1.1.5655. And then last but not least, we should what this? So last but not least, we should what this? And I'll write the other decimals, 5564. Last but not least, we should what this to get our answer. So last but not least, we should what this? Because we're not looking for r squared. This is a very good, tough question. It's a little good bit of mathematics. So we say, like, find the two strongest correlates, square root. Yep. So now we need to square root this, which will just give you r right there, and then square root. It's a good algebra conceptual problem. Like, if it was pure algebra, like, if we just give you the numbers and we say solve this, but then if you have to know conceptually what are these things, and then like, it's a good kind of like, it's a really tough problem, level 10 problem easily. If you didn't get this problem, I think very few people got it. But you know, you got to have some challenging problems. We don't want to make the whole test like algebra related, but the idea of what are you doing is the most important part of this. It's not just solving an algebra problem. It's like, what am I given? I don't think we have this type of problem on the test again. There's sometimes just a few pretty tough problems. Like, and you know, you don't teach directly to them, but conceptually, we should know what the variance inflation is. The variance inflation is 1 over 1 minus r squared. So if we give you values of variance inflation, it is this. And then we're literally doing a solve for x problem. Like, this might as well be solve for x, but we don't actually want x. We want square root of x. Does that make sense? Like, we want square root of x, not x. Does that make sense right there? This is, once again, probably one of the toughest problems on the first test. It's a solve for x problem, but we're looking not for x, but for square root of x. And so we can confirm our answer right here. So 1 over 1.565564. There goes that. 1 minus that is that square root. And so that is this right here. Let's go here to correlation. So core of survey 10, height, and survey 10. Wait, these are base functions in R. And there it is. And look at that. Almost even down to the last decimal. Down to the last decimal, we found the correlation. So it's like I said, it's a bit of an algebra problem, but the reason I like it is because it connects the concepts of, like, what is variance inflation, what is r squared, what is correlation. And so these are things we have to know. Like, well, correlation, if you square it, you get r squared. The r squared sub I is the correlation, or is the r squared for the ith variable. We can use that to find the variance inflation. Really tough question. I think very few students got it. Like, probably like 5 out of 150 students. But one or two questions like that is all right. You don't want the whole test to be like that, and this is a bad whole test. Then you got to do a bunch of curving. But yeah, very tough conceptual question. And we've got the solve over here for it. When we know the variance inflation for the largest, going through, putting that in, and solving it. We like curves. We'll just make the whole test impossible, and then we have to curve to the naive model, right? So we have to curve to the historic naive. So let's end with that question right here. I do like learning on a mathematical rather than just code. Exactly. We don't just run code. We need to know what's going on. And so if I were to say, well, we'd probably have to curve everyone to the historic naive, what am I saying? Everyone would just get the what? If I said, well, if for some reason everyone got zeros, I guess we would just curve to the historic naive. What would we be doing? What am I telling you right there? We'll end on this note. It's not our goal, but if everyone got zeros, we might just have to curve to the historic naive. What am I telling you? I could just talk like a normal person and say what? Normal person. Never been good at that. So what could I tell you instead? Instead of, since everyone got zeros, we have curved to the historic naive. And then I say, if you know what you got, if you can explain what you got, you get that grade. You might be happy with that. You might not be. If I say historic naive, I'm telling you we'd just be using the what over previous years. Which is kind of what we expect, given nothing's going on. Almost like a null hypothesis. Last question of the day. Puppet Shark. The average, Matt, getting some points for the class. You're all right, Matt. Yep. The average, the historic naive would be, you know, the data. Publisher, what are you doing, man? Saying, yeah, over me. Is today? Today is that day. It's Wacky Wednesdays. With that, everybody, we'll be back streaming some Tool 1 later. Bye for now, everyone. Bye, Wacky Wednesdays. Wacky Wednesdays. Bye for now, everyone.